we're going to go over Boyle's and Charles' law. This is Mr. Boyle, and his law has to do with the pressure and the volume of a gas. And he said if you have a gas where temperature and the moles of gas are constant, that if you increase the pressure, that the volume will decrease, or vice versa. If you decrease the pressure, then the volume has increased. He said they are at an inverse relationship, and that mathematically is what this table shows. So for, I don't know what gas this is, it doesn't really matter, but if the volume is 10, the pressure is 760. The volume is 20, the pressure is 379. And as the volume gets bigger, the pressure gets lower. And thinking about the computer lab, this makes sense because it's a bigger box, so there's more space for the particles to move around. And if you remember, pressure is a result of the particles colliding with the walls of the container. So if there's more space, they're not going to hit the walls as much because it's a big space. And then it's a opposite or inverse relationship. So you need to know this formula. I would probably write down that it is an inverse relationship. As pressure goes up, volume goes down, vice versa. And I would also draw this graph. That is the graph of an inverse relationship. And that shows, over here at a really big volume, the pressure is super low. So we're going to do some Boyle's Law example problems. Okay, so the pressure of a 3.5 liter balloon was determined to be 1.5 atm. Assuming temperature remained constant, what would the volume be if the pressure was decreased to 0.5 atm? So this is Boyle's Law. It's pressure and volume. P1 V1 equals P2 V2. P1 and V1 stands for my initial pressure and initial volume. So my initial pressure, my P1, is 1.5 atm. My initial volume, my V1, was 3.5 liters. And then I'm looking for my new volume, so I'm looking for my V2, and my pressure was decreased to 0.45 atm, so that's my P2. You're going to have a lot of gas laws, and so if I were you, I would write out your variables. That'll help you pick out which formula you're going to use, because you're going to have like 8 formulas. And then you need to check. So pressure can be in any unit as long as it is the same unit, and pressure is in atm. Same with volume. Volume can be any unit as long as it is the same one. And our pressures are in the same unit, so we can plug this into the equation. So my P1, 1.5, times my V1, which was 3.5, equals P2, 0.45, times V2. We don't know. First thing, multiply those numbers. And that is 5.25. equals 0.45 times V2. And so we want to solve for V2 and get V2 by itself. V2 is being multiplied by 0.45, so to get V2 alone, we're going to have to divide each side by 0.45. That means that those cancel out, and V2 equals whatever this is, and I'll go divide that, and my V2 equals 11.67. And then the unit for V1 was liters, so the unit for V2 has to be liters. And then significant figures still matter. When I look back at the problem, all of my givens were 2 significant figures, so I would round that to 12 liters is my new V2 for my final answer. And that is Boyle's Law, pressure and volume. Charles' Law has to do with the relationship between volume and temperature. And this is assuming that pressure is constant and the moles of gas are constant. And this is his formula. V1 divided by T1 equals V2 divided by T2. Now, something you should know in Charles' Law. Temperature has to be in Kelvin. It can't be in Celsius because you can have a -degree Celsius. Like you can have -10 Celsius. If you plug a -10 into that equation, that would give you a negative volume. And that's mathematically not possible to have a negative volume. And then this is my graph of volume and temperature. I would draw that as well. Now looking at this graph, as temperature goes up, volume is going up. That is a direct relationship. And that is mathematically what's shown in this data table. When the temperature, as the temperature goes up, 273, 298, 323, etc., the volume of the gas goes up. And why this happens, if you remember, temperature is a measure of the average kinetic energy. So if the gases have a higher temperature, that means they're moving faster. They have more kinetic energy. And they would take up, if pressure is going to stay the same, they're taking up more space because they're moving a lot faster to keep the pressure constant. So this is Charles' Law, V divided by T. Boyle's was P and V. Dalton's was just pressure. Okay. A balloon has a volume of 5.6 liters at a temperature of 98 degrees Celsius. If the volume of the balloon increases to 9,500 milliliters, what will it be the temperature of the gas in Celsius? And we're going to assume pressure remains constant. So let's list our variables. My V1 equals 5.6 liters. My T1 equals 98 degrees Celsius. My volume increased, so my V2 is 9,500 milliliters, and I'm looking for my T2. And the equation, V1 over T1 equals V2 over T2. You would know this was a Charles' Law problem if I didn't tell you, because it's temperature and volume. Boyle's Law is pressure and volume. Okay, a few things before we can plug this into the equation. We have to change temperature to Kelvin. So to go from Celsius to Kelvin, you add 273. That is 371 K. And then our volumes are not in the same unit, and they do need to be in the same unit. If it was me, which I'm going to do it anyway, I'm going to change V2 to become liters instead of milliliters. I don't like to deal with numbers in the thousands if I don't have to. And so to change this, there are 1,000 milliliters in 1 liter. And so that would be 9.5 liters. Now, talking about, we just said this is a direct relationship. If V1 is 5.6 and V2 is 9.5, volume has gone up. And so the temperature should go up because volume and temperature have a direct relationship. If you get an answer with a temperature lower than 98 degrees Celsius, you did something wrong. But we have our variables written, temperatures in Kelvin, volumes in the same unit. We can plug into the equation. So V1, 5.6, divided by T1, 371. Remember, the temperature has to be in Kelvin. equals V2, 9.5, over T2, what I don't know. There are a few ways you can solve for this mathematically. If it was me, I would use cross multiplication, and I think that's what y'all learned. So you're going to multiply these two together. So 371 times 9.5. I'll write that down here. 371 times 9.5 equals, and then you're going to multiply these guys together. 5.6 times T2. First, let's take care of this side. 371 times 9.5 is a big number, 3524.5, and that equals 5.6 times T2. Now, we want to solve for T2 to be by itself. It's getting multiplied by 5.6. I'll divide each side by 5.6. That cancels out. Now we have, run out of room, T2 equals 629.375, and that unit is Kelvin. Now, the question didn't ask for temperature in Kelvin. It asked for the temperature in Celsius. So we would need to convert this back to Celsius, and then we would have our final answer. And if you have Kelvin to go to Celsius, you're going to subtract 273. And when I do that, my T2 equals 356.375 degrees Celsius. And then with significant figures, looking back at the original problem, 2 sig figs, 2 sig figs, so it'll have two significant figures. I would make that number 360 degrees Celsius. And then do a check. Does that make sense? Original temperature, 98. Original volume, 5.6. New volume, 9.5. New temperature, 360. Yes, our volume increased and our temperature increased. So that would be correct. You're now going to complete page 5 in your packet, which is some are Charles' law and some are Boyle's. Again, Boyle's P1 V1 equals P2 V2. Charles V1 over T1 equals V2 over T2. And remember, temperature must be in Kelvin.